Several applications we've considered of flux spinning are some non-contacting mechanisms, including prismatic, cylindrical, and revolute joints. Last year, we presented the demonstration of a revolute joint on an air table, shown here, because these joints generally require several unrestricted degrees of freedom. The air table was our first attempt at testing this kind of setup. You can see the YBCO superconductors, permanent magnet, and 2 electromagnets on some glass plates levitating on an air table. Now, though we successfully demonstrated the revolute joint, there were several disadvantages with this air table system. There's a very small working space defined by the size of the air table and the amount of pressure it takes to cover the entire surface with air coming out of it. This also contributed to a very low payload capacity for each of our test modules. Due to the low pressure of the air coming out, you can't put too much mass on each individual piece of glass here to float. Also, the air table surface gave us a fairly uneven floating of the modules. Any kind of material imperfections would cause the modules to slide in a preferred direction or stick or some of these other issues. So we decided to come up with a new way to test out some of these flux spinning ideas. And we call this the Flux testbed. This is a individual vehicle-based testbed where the vehicles themselves provide the levitation rather than the testing surface. So our goals with this testbed included the testing of some basic flux spinning mechanisms similar to the revolute joint, which you saw in the previous example. We also wanted a testbed that would allow us to verify some of our mission hardware. We've used CubeSat-sized modules, which are 10-centimeter cubes, in some of our flight missions. And we also use a half-cube design, which I'll mention a little bit later, in our recent microgravity flights. And we wanted to be able to mount the completed equipment on a testbed to run through some of the actual experiments we wanted to run in flight in the laboratory setting. We also felt it was important that we could rapidly reconfigure the test vehicles so we could change out experiments very quickly and try new ideas as things worked or didn't work in the lab. And we also wanted to make sure that the vehicles were low cost so we could quickly implement a large number of these to work on multi-modular systems, which is an important part of flux spinning research. So the first part of the Flux, and perhaps the most important, is this base segment, which you can see in more detail here. This consists of the air system and the levitation mechanisms, and I'll be going into some more detail on the individual segments in just a moment. The next segment of the Flux is the payload segment, and this has 3 general configurations that we've been using. A mostly empty platform as a component segment, which allows us to mount individual components like actuators, electromagnets, permanent magnets, these types of things that we want to investigate their individual performance. We can quickly attach them to this type of segment. Our microgravity flight uses the half-cube architecture, as I mentioned. The entire size of the module is a 12.5-centimeter cube, and we divide that up into 2 half-cubes, which you can see here, that can easily be slid apart and accessed for changing out experiment types. Since we use this design as a standard in our flight missions, we wanted to be able to just put this right on our vehicles. So we developed this half-cube segment as a way to do that. And then, as I mentioned, we sometimes use CubeSat-sized hardware. The payload segment can also adapt to a completed CubeSat-sized vehicle, so we can put our completed hardware on the testbed to evaluate its performance. Finally, there's an optional electronics segment that is present in some of the CubeSat, or the Flux variations. This consists of some standardized hardware, which I will mention shortly, that provides more functionality to component level testing. And as you can see, this is one assembled variation of the Flux on the testing surface during some of our recent experimental tests. So the way the segments interact with each other is as shown in this diagram. The first is the base segment, which, as I said, contains the levitation system, and that is mechanically connected to one of these 3 payload segments. They're all shown here, but only one of these would be implemented on each individual Flux vehicle. And then this This payload segment would be mechanically connected as well to the electronic segment if it was implemented. Generally, when we're using half cubes or completed CubeSat size modules, they contain their own mission-specific communications and power and any other electronic systems, so the electronic segment would not be used. But generally, during the component level float cube testing, they're simply magnets or actuators by themselves, so we have a standardized electronics package that can provide power and a data connection to these actuators. So this would be one individual float cube vehicle. And then this vehicle is part of the larger test setup. We can have 1, 2, or really any number of individual float cube vehicles limited by the size of the testing surface. Currently, our testing surface is about 1.5 square meters. Then the float cubes physically levitate off of the testing surface. Here, there's a motion capture camera with a view of the surface which can take images of the tests in action for later analysis. That feeds it to the computer. The computer can also communicate with the individual float cube vehicles to send in commands, run through routines that we want to see, and so forth. And then the float cube vehicles themselves commonly have wireless hardware that let them communicate with each other in case they want to perform some sort of synchronized maneuver. So that's the general layout of our test setup. Now the individual float cube vehicles, as I mentioned, have the 3 segments.